Hello, we are Team 7, and our senior design project is Damaged Satellite Repair Solution. Team members on this project are Braden Butler, Zachary Whitlow, Dustin Robbins, and Alaweed Alahimi. Our advisors are Dr. Masad Rabi, Dr. Oy Ma, and Dr. Andrew Barth. Contents we're covering in this presentation include the problem statement, the solution to the problem, cost estimation, project schedule, concept map, high-level system drawing, flowchart, and conclusion. Problem statement.
So our problem statement, as we all know, the United States and many other countries have all kinds of numerous satellites up in space. And many of these satellites we actually don't even use anymore because they have problems or they're outdated or whatever may occur with these unused satellites. And we have no way of getting anybody or anything up to these satellites to be able to repair them or update them or fix them. And because of this, we spend a lot of money building new satellites, and instead of fixing satellites, we spend a lot of money just sending new and improved satellites up, which could be wasting money instead of sending something up there to fix the satellites that we already have up there. We're just sending more and more and more satellites up, which also causes a lot of space debris with all of the older satellites that are no longer in service. Currently, Dr. Andrew Barth has already developed a prototype called the Repairman, and is a satellite that functions as a proof of concept for such a device. But certain electrical aspects need to be improved to make it more of a realistic approach.
So our solution is going to involve utilizing the existing prototype's features and also building upon the known issues that Andrew Barth has talked with us about. We're going to build a completely new prototype that will better serve as a proof of concept for the Repairman satellite. Specifically, we're going to investigate and solve issues revolving around an improved design for the overall structure. This also includes developing a more divided approach to our electrical design, with having low power, medium power, and high power, with high power being 12 volts. And also has to do with the distribution of the air canisters. We're going to be investigating better weight distribution overall. We're also going to be adding in electronically controlled air pressure regulators. Currently, there is no way to determine the exact PSI that we are sending to the air thrusters that allow the prototype to levitate around the table that it's going to be sitting on. And you have to do that manually. We're also going to be implementing a better distribution of voltage levels with additional battery capacity. We're going to use, the whole system will use DC current, and we're going to be utilizing DC step-down devices that will allow us to better distribute the voltage. We're also going to be looking at adding enhanced graphics processing units for the position tracking software that we're going to improve upon. And we're also going to implement a robotic arm for catching the damaged satellites. This is our current design, or not our current design, rather the current prototype that's in use. On the left, it's an overall picture, along with on the right. And in the middle, we have a closer up of the different processors and relays that we are going to be improving upon.
So the project schedule is, as you can see, what we have been working on so far. So we pretty much broke down each of these into smaller categories for each of the different layers of this robot or satellite that we are trying to recreate. So we have already spec'd out quite a bit of all of these different electrical components and different mechanical components that are going to be going onto this as far as we have come. Go and go to the next one. And then as you can see, we have spec'd out quite a bit of the electrical components as far as the mid-level and high level. And then as we get further on into November and December, we're going to continue to spec out and make further decisions on the design and eventually start creating it next semester.
This slide shows the cost estimation for this project. The total initial cost is $1,723. This is calculated before the taxes and shipping fees. This project funded by the IRAS lab. Also had to mention most of the parts has been purchased by the lab. So here's we can see the additional parts and prices. One significant price is the 80-20 aluminum frame, which we are using to build the structure of this project. Here we can see the concept map. So the senior design project is a combination of different classes, courses were taken throughout UC, also using our co-op experiences. So we can see concept map layouts, an overview of this project, and shows how the hardware and software interface with each other.
This is our high-level system drawing. All the electrical components are controlled by a Raspberry Pi, and the Raspberry Pi also controls the Arduino device that regulates the air pressure going to the thrusters found on the top of the device. We are planning to add in the robotic arm specifically, possibly a reaction wheel, Jetson GPU, and also LiDAR. Further, we are also looking at adding in new battery components, and we will be able to electronically monitor the power consumption and battery life to better understand how we are utilizing our power and making sure that everything works on the final product as we expect it. We also have the DC to DC converters to step down the voltage as needed. And on the bottom left, we have our air pressure regulator that we are also going to implement.
So this is a flow chart that shows the program or the software operation of our platform. So it basically has two components: the interrupt side and the main listening and execution loop. So on the left is the main loop, and essentially as you work your from the top and go to the bottom, the Arduino is the Raspberry Pi is listening for a command to come over the Wi-Fi network in the lab. If it receives a command, it goes ahead and parses that command. And I thought it would be a good idea to implement a cyclic redundancy check, just to make sure there's nothing getting interfered with noise and things like that. And then if the CRC and the packet structure is valid, we're going to go ahead and send back to the transmitter a acknowledge packet saying, yep, everything's good to go. And then after we transmit that, we're going to interpret the actual type of command as well as any parameters that it might come along with it. So like it might receive a movement command that says, I want to move so many inches to the right, or or it might receive some other command that says read data off of this component and then transmit that back. So after it interprets that, then it just executes it, like I said, initiates the proper thrusters if it's a movement command, or reads data off of sensors if it's like a data acquisition command. Now, as far as the interrupt side, that's over on the right, and basically those two diamonds at the very right show when our main listening loop might get interrupted, and basically that is if an object is detected in the immediate vicinity that might need to avoid, and if so, it interrupts the program and executes whatever object avoidance protocol that we want. The other thing is if we do have an electronic pressure regulator, then we can monitor the state of the pressure and then interrupt the program and say, hey, the system's not behaving like it should, and from there we can either shut it down or fire the thrusters longer, or whatever the case may be. Next, thank you. So in conclusion, our upgraded platform is hopefully going to provide the lab with a more realistic zero gravity or low gravity frictionless environment. And some of the things that this can help the lab with is new and better research. So if you have a better analog to space, then you can have more accurate propulsion system design. You can have better like thruster algorithms that can avoid obstacles. You can start experimenting with torque rods and reaction wheels. And you can also, like with the robotic arm attached, you can implement sort of control theories as far as the dynamics, as far as mounting a robotic arm to a space system. And then an additional application, like Dustin mentioned at the beginning, is the removal of space junk, which can be on top of the idea of repairing existing satellites. Maybe it could, in the future, implement some sort of program or protocol that would eject space junk from orbit. And so I think that's it.